to this picture again here. Spectrum. Somewhere there is mobility H. And my tau squared is somewhere here. So eigenmodes in this shaded region are willing to get some non-zero term. They are linearly unstable. Now, as long as width of this region is epsilon naught. Now, let us cool down. We will get more and more states which are unstable in this sense. So we move this boundary. And eventually, at sufficiently large temperature, such unstable modes are independent completely one from another because we are living in different parts of the space, localized clusters. Of course, we cannot lead to real freezing because each of them contains only finite number of spins. These are just what is called superparameters. You get some. In each of this region, you have some number of spins which are locked together. Even not exactly spins locked together, but some part of the spins are locked together, and the dynamics is described by the amplitude scaling. Now, very important point. We decrease temperature, number of these regions grow, they start to overlap. At this point, we cannot anymore consider each area of each eigenmode separately one from another, because we interact. But here, because the system is random, there are two different types of interaction of quite different magnitude. One interaction is like this. Here you see squares of two different eigenmodes, which is a positive object, and also matrix element is given by psi squared and psi squared. So everything is positive. But this part of free energy does not depend on signs of these amplitudes. Actually, A lambda, I can write down in the following way, like sigma lambda, A lambda modulus. So it is a real number, it can be positive or negative. And it can be characterized by its absolute. This sigma lambda will be my effective spins later on. Again, these are variables which plus minus. But these variables do not enter such terms in the reality. This term depends only on the absolute value. There are other terms, for example, like this. Here you see three different eigenfunctions and three different amplitudes. One goes in square and two others in linear order. This matrix element contains sign or alternating terms. So it is much smaller, just as a smaller by factor square root number of these terms. And it depends on sigma lambda and sigma mu. There is some range in temperature or in reduced temperature tau, where I can neglect second type of terms and consider only these even ones. Questions? Everything is clear. Unexpectedly good. Let's compare with the usual situation. In the usual situation, you would have in a similar quadratic term dependence like this. So again, if there is a tail, there are some localized eigenmodes which are stabilized by this usual quadratic term. And in a usual like a ferromagnet situation, there is no hierarchy of interaction. All interaction, even and odd, have matrix elements of the same order. Good. Now I go with temperature down. So T is negative, and the modulus of T is larger than this epsilon naught square Z minus 2/3. In this expression, I collected all even terms and neglected odd parts. So the effect is that because of interaction, I have a shift here. Instead of just tau, I have some additional terms. And I have also 6 odd terms. To account for this interaction, I can introduce a kind of local field called B, which is made out of squares of my amplitudes and squares of wave function. All terms here are positive. Then it means that when there are many terms in this sum, here this B is a relatively constant quantity. Of course it fluctuates, but these fluctuations are small in comparison with this average B. So what it gives me, and eventually I want to find my amplitudes. Equation for this amplitude is here. I take a variation over A lambda, I get this term, and this term with renormalized equation. Remember, tau was negative. But when I add that interaction, it becomes positive. Because the solution of this equation gives me that B is close to modulus tau. So this term is positive. What is this picture? I have many eigenmodes. Each of these eigenmodes by itself is unstable in linear approximation. So I should fill it with some A squared. And also they interact. This interaction leads to renormalization of coefficients. This is what can be called as a superparamagnet. Each amplitude is given by the expression A lambda squared for the modes where epsilon lambda is larger than psi, and psi is with tau plus B squared. This psi is something relatively small but positive now. Then I should explain what is V. V is a participation ratio. Usually we discuss inverse participation ratio, which is just sum of psi to 4. Now, crucial point is what is the distance in energy between the age of our unstable modes, psi, this is the age, and the position of Anderson mobility age. We know that somewhere here there is a transition from localized to extended state. And when we approach this transition, localization volume grows as a power law. Zeta is this normalized proximity to the mobility age. The self-consistency equation, remember B was defined like this. B was made as a sum over all these eigenmodes. So I should find the self-consistency. The self-consistency comes with such interval over spectrum. Density of states is approximately constant near mobility age. I was saying it exponentially drops. Yes, it drops here. But now I'm interested in the vicinity of mobility age. In the vicinity, nothing happens to density of states. It is some constant, we can estimate it. The key point is the following. When we approach mobility age, volume of localization grows with some exponent. And we need to take this integral here with volume and also with this epsilon minus a. The rest crucially depends on relation between theta and 2. If theta is larger than 2, then as long as we cool down, tau grows, zeta goes to 0 but never reach it. Because for theta larger than 2, there is a negative power here. So with decrease of temperature, which means increase of modulus of tau, we are slowly approaching mobility age. Approaching in the sense that the unstable modes who are separated from stable mode by this point, this boundary moves here. If theta is less than 2, then at some finite temperature we will approach mobility age, and what we will get is roughly the same thing as if you would consider, say, a ferromagnet with some disorder. You will have a condensation to some extent. Below, on the left of this boundary, all modes are extended, and the most close to this age, it is already extended mode with infinite volume, so you may have microscopic condensation into this mode. As long as you are still here on the right of this age, you have kind of local clusters, but they are only local. Is it clear?
Well, to me, yes. I don't know about others.
Okay. So,
but what is the, so where is the glass transition here? TC?
Wait a moment, you will see. It will be seen after some time. If, let me put a comment, if theta would be smaller than 2, then glass transition would be at some tau where this zeta happens to become 0. and we got microscopic condensation of modes.
Okay.
My point is that it seems that, I think, that actually theta is larger than 2.
Okay.
And if it is larger than 2, we never come exactly to this stage.
What
We
is
can
the-
only approach it.
What is determining theta again?
Theta,
Or is the localization?
it is localization exponent. Well, when we did all that in 84, 85, knowledge of these localization exponents was relatively poor. Now, what we know, nu is a standard exponent which tells us that localization length scales as E minus EC with exponent nu, and then D2 is another exponent which is quite well known for mobility age. And our theta is a product of nu by D2. For example, from this paper of 2015, there is a for orthogonal ensemble, D2 is 1.23, nu is close to 1.6, so the product is 1.96. Basically, one more point is the following, that this, then they determine this fractal dimension D2. They study statistics of inverse participation ratio. So average of inverse participation ratio. What we need here is average of the inverse thing. It is not guaranteed that the exponent is the same. Moreover, it seems that they are different. So, I mean, it seems that G2 defined via volume itself would be a little bit larger. Anyhow, we are on the border in the sense that this theta is somewhere close to 2, maybe larger. And let me show you what will be the consequence if it is indeed larger. If it is larger, we cannot get directly to the edge. So what happens instead? And if theta is equal to 2, again it is the same, just zeta will be exponentially approaching 0. Now it is a time to recall that we have other terms in the free energy which was neglected, namely the terms which depend on these sites. Suppose we make this all this minimization procedure with we find all squares of amplitude as found with self-consistency equation which I discussed on previous slides. But still we have degrees of freedom, signs of this amplitude. Energy depends on these signs by this way, which reminds us the original Hamiltonian from which we start. In the original Hamiltonian, we had sites I, J, and couplings between them. Now, instead of sites, we have these subscripts lambda and mu, which corresponds to eigenmodes of our interaction. But again, we have this kind of coupling. J I lambda mu is given by this kind of sum, which is evidently random. Psi is alternating. Delta B is something which is difference between actual B and average B. So this is the sum of terms plus and minus, which are equal to some random. So what we get? It is a superparamagnet with effective spins which interact again in the same way as our original system. It seems we can produce a kind of discrete renormalization group procedure.
That's what I wanted to ask you. Since you are interpreting your lambda as a sort of generalized space, so if you take it as a continuous space, can't you just do some plain epsilon expansion on your? No, why not? I mean, you get an action that depends on a lambda.
Which epsilon expansion? It is. I mean, it is.
You have an
It is
action.
a crucially discrete procedure.
Why crucially discrete in the thermodynamic unit?
Well, let me put it in a different way. Epsilon expansion starting from what?
Well, that's a good question. Well, I mean, naively, my question from about the epsilon expansion originated from seeing that 8 lambda to the 6th power that usually you don't include in the 5 to the 4th because it's relevant, but it's much less relevant than 5 to the 4th.
Look, for there are some attempts to construct field theory for spin glass transition in terms of without this expansion of the basis and using, for example, replicas from the very beginning. As far as I remember, the upper critical dimension was found either 6 or 8 in different papers. So the relation of this to real three-dimensional space is very, very much unclear.
I have another question. So here you're essentially passing to the level of modes, and then you write down an effective something in terms of these modes. Now, is there any way to see a relation between this and the standard mode coupling theories people standard? Sorry for building. I mean,
I
also
don't,
in the language of mode coupling is something that's generically used for glasses, for pattern formation, for all kinds of static problems.
There is some relation, but indirect. For example, mode coupling equations for usual glasses, they are not like this case. They're more similar to mode coupling for p-spin models with p larger than 2. They, in a sense, they are monolinear.
Okay.
Here I'm using, to a very large extent, I'm using expansion in terms of eigenmodes of my original matrix,
Yeah.
JAJ. And in this mode coupling which you ask, in a sense, there is no such eigen
No.
expansion at all.
Yeah.
So in terms, ideologically, it seems to be simpler, I would say.
Yeah, I would say so.
But what we will get? So this effective matrix element is some like this. Yeah.
Why these effective matrix elements have the same probability distribution of the original random matrix?
No.
In order to have
No. I only say that it is random.
but not with the same two.
What I need is to at least to find variance.
Yeah.
I assume it is a random variable, and I should estimate variance of this random matrix element. This is what I will show now. Of course, I assume that again this matrix E lambda mu has effectively a large number of neighbors, like my own original one. If it is so, then the only real parameter I need is variance. So let's look. This is a variance. I take a square of each of these matrix elements, sum over all lambda, and it will be analog, this J1 squared will be the analog of my original J0 squared coupling strength, which I put just one from the beginning. Now, as long as I approach my age between unstable and stable modes, as long as it approaches mobility age, which means this zeta decreases to zero, they both effective number of neighbors and effective coupling grows as some power, one power kappa, another power here is phi, and this estimate z to power minus 1/3, it is, I will show the next slide, it is, if I am somewhere in between at zeta further 1, then I can estimate all these terms. So tau for the tau naught means zeta for the 1, then I can estimate all terms which enter this matrix element. Combining all these factors, I find typically matrix element is relatively small. Good, but when I cool down and my boundary moves to mobility age, both with matrix elements and number of terms grow. What are these exponents? I don't know exactly. I mean, some simple estimates from scaling would give me this numbers. So they would be related to my major parameter, theta. But this is naive estimate, and it should be checked numerically to know really what it is. So when this zeta decreases, effective coupling grows. Eventually, it will grow up to something of order unity. It becomes of order unity, then zeta is equal to some zeta 1 expressed in terms of my original number of interacting neighbors and exponent phi. Okay, now let me check what is the effective number of neighbors of each of such a state. it is here. It involves another exponent kappa with my naive estimate, the whole combination is this. Now imagine that theta is a little bit larger than as it seems to be. Then it is quite probable that the whole combination, which stays here, is larger than unity. Actually, it is a very important point. What happens if it is larger than unity? Then my renormalized problem with effective spins sigma instead of original spins. It is of the same type as original model. In the original model, I assumed that my coordination number z is large. If this exponent larger than unity, then okay, new effective number will be even larger. It means I can go on and repeat again and again this transformation from spins of a level, say, n to spins of level n plus 1. And then we see a very funny situation. Here, this T naught was original mean field approximation for the temperature where something becomes critical. Tau naught was this width of the region shown here. Now, we move sufficiently low in temperature to get to the temperature T1, where effective spins, sigma, start to interact strongly. This is how we come to the same exactly problem, but on a level of this superspace.
So you do it again.
So we do it again. If effective number of interacting neighbors was increased after this first stage, it means my width tau naught will become smaller. So next temperature T2 will be closer, the distance will be smaller than this one. But eventually it will be a sequence of these discrete RG transformations, which has some accumulation point at some finite value of temperature.
But did you calculate this? Did you calculate it for some example?
Yes, we calculated it it is written in our review book, 1990, under some assumption about this exponent. So what happens is that distance between these points decreases, effective number of interaction neighbors increases, and the actual transition happens in a very strange way. It happens as accumulation point of this approximate singularities. It is very different from usual scaling picture to which, say, epsilon expansion might be useful. On the other hand, to what it reminds, in some sense, is a quite well developed later on technique of strong disorder normalization group, which started by Daniel Fisher and for one-dimensional quantum eigenchain.
Do you have a stationary distribution for your disorder?
I don't know.
That's what you get for.
Yes, I don't know. We did not come back to all this story after this long time. I would maybe like to come back because I feel that what we did 40 years ago was interesting but unfinished.
Unfortunately some kind of antiquary degust.
What?
Well, degustazione antiquaria, I don't know how to say it in English. So,
So,
So at each step you recalculate the variance and then check if
yes.
the
At each step, we again calculate variance of matrix elements, check what is the amplitude, check what is effective number of nearest neighbors. As long as it grows, this scheme is self-consistent.
Yeah, no, my point, which is related to what I asked before, it's if we have the interaction, I don't know if only the variance if the distribution is Gaussian or
You mean that distribution can be
Can be
very non-Gaussian?
non-Gaussian. So then,
My main assumption was that effective number of neighbors, interacting neighbors, is large, which implicitly assumes that Gaussian, that second moment is sufficient. Of course, it could be some very non-trivial distribution which cannot be described just by second moment. It happens. Should be checked, I don't know. So the closest analogy of this procedure is with what is well developed is with strong disorders. Now how it looks like in a picture, say. That was expansion of our magnetization in terms of slow amplitudes. I is some point of observation point. So magnetization at this point is depends on amplitudes of many eigen amplitudes A lambda of all eigenstates which has considerable weight in the point I. There are many of them in principle. So this is why I call this picture fractal clusters. Usual picture of, say, superparamagnet is that you have some collection of spins which are strongly coupled. There is the average moment which fluctuates, and other spins are sitting in other clusters. Here it is different because eigenfunctions psi, which are relevant for magnetization at some given point, belong to wave eigenfunctions which may overlap each other rather strongly. So Mi depends on many different amplitudes. Now, when we go to next stage of hierarchy, each of these amplitudes itself becomes a function of some eigenmodes of a higher level, and so on and so on. This is, again, it is still another way to find a hierarchical organization of modes. Again, how it is related to Parisi scheme, I don't have any idea. I don't have any idea. It would be interesting to understand, but it is not so easy to understand because Parisi scheme works for mean field below TC.
And this works above.
And this is a picture above this.
So here it would be a replica symmetric, the Parisi.
In terms of real thermodynamics, it is replica symmetric. But if we look at some finite time scale,
But Misha, can't you understand this as, we know for superconductors that above TC we have superconducting fluctuations
Mhm.
described by as
Yes.
Larkin, whatever, etc. So isn't it something similar, glassy fluctuations
of course,
in a paramagnet?
Of course it is similar. What is not similar is that in a superconductor or in a ferromagnet, you don't have any hierarchy.
Okay.
You have just some classification of modes in terms of wave vectors, and
But-
that's enough.
But in a superconductor, we know what are the manifestations of those fluctuations. You have, for example, the quasi-gap where is slight suppression of density of states.
Mhm.
So here, how would you see this?
Here I can see it in two ways.